Hello, so what I want to do today is I want to solve the equation governing the RLC circuit that's driven by an AC power supply. I've already applied Kirchhoff's loop rule, or the modified version of Kirchhoff's loop rule, to solve this problem. So I have the power supply voltage as V cosine omega t, so the circuit is driven by this power supply. The voltage drop across the resistor, the voltage drop across the capacitor, and of course the voltage drop across the inductor in my expression. So I know that, since I know that I is dq over dt, and to be consistent, I really should make these small letters because we're looking at the time dependence of these equations. So I kind of bucked the convention that we've been using. I apologize for that, but we're trying to solve for I as a function of time, really. And what I'm going to do is actually solve for q and then get I, because I know I is dq dt. I also know that since I is dq dt, di dt is equal to d2q over dt squared. So what I'm going to do is substitute those into this equation. And I'll get the following. V sub m cosine omega t minus r dq over dt minus q over c minus L d2q over dt squared equals 0. And what I'm going to do is try to solve for q here. Let me rearrange this equation. I'm going to move all these terms on one side of the equation. And I'll put this term first. Okay, and one more thing. I'm going to divide both sides by L. So I'm going to do it very quickly. Divide both sides by L, and I get that for my equation. So this is a second order differential equation. In fact, it's an inhomogeneous second order differential equation. And there's constant coefficients in front of it. And there's actually two solutions to this. One of the solutions is the case where this is 0, and it's called the complementary solution. And the other solution is actually the solution to the inhomogeneous case. So my total solution is written like this in terms of two terms. This is the complementary solution, so it's the solution to the homogeneous case. We did this problem about a week ago. This is the transient solution. We talked about the transient solution to the RLC circuit. That's the term. And then this term over here, this is called the particular solution. It is the solution to the inhomogeneous case. Which means that this term is not 0. Okay? And this represents the steady state case, or the steady state solution. And we already talked about the transient solutions last week, And so, we talked about the underdamped, the overdamped, and the critically damped, etc. We talked about those. I'm not gonna go over them this time. I'm really interested in the steady state solution. So I'm really interested in Q sub P. And in fact, if you wait long enough, this term goes to 0. This is an exponentially decaying function that goes to 0. And really, I'm looking at the case where a long period of time has elapsed. This term is 0, and Q sub T equal Q sub P. So I'm going to look at this solution. That's my goal. So I'm going to take a minute here. I'm going to erase the board. I'm going to stop the video. I'm going to erase the board and rewrite some things. Okay, so I erased the board, and I'm going to continue now to come up with the solution. And again, I'm looking at I'm really going to focus on the steady state case. Moreover, you can think about maybe a long time has elapsed, so we don't have to worry about the complementary solution. So the question is, how am I going to get Q? Well, I'm going to actually use some intuition to get Q. I know from experience that the current through this circuit is shifted by some angle phi relative to this, to the power supply voltage. I also know that the current is the derivative of the charge. And so I'm going to guess the following function. So that when I take the derivative of this, I'm going to get something times cosine omega t minus phi, which is shifted from this function by an angle of phi. That's why I'm choosing this function. I could have easily chosen cosine here, but then it would be hard to interpret the phase shift. Okay? I'm doing it so I'm consistent with how we've been describing the circuit. That's why I chose this function. All right. And I could have made this a plus too, but again, I'm trying to be consistent with how we've been describing things so far. And what I'm going to do is I'm going to take this and stick it into the equation. So I want to make one substitution first. We know, because we've talked about this, that the resonance frequency is 1 over the square root of LC. That means omega naught squared is 1 over LC, which means that this term over here can be written as Q times omega naught squared. Okay, now let's stick that expression into this equation. And you'll see there's going to be a lot of algebra involved in here. Okay. Now I got to take the derivative of this with respect to time. Now taking the derivative of this with respect to time is not hard, because when I take the derivative of this twice, I'm going to get the same function again times a constant. So when I do this, I'm going to get minus a omega squared sine omega t minus phi. When I do this term, I'll get r over L, a omega cosine omega t minus phi. And then I just have this term. What I'm going to do is I'm going to collect these two terms together. So let me rewrite this. And when I collect these two terms together, I'm going to plus Okay, so what am I doing? Well, my goal is, what I need to do is to figure out what A is and what phi is. I need to determine an expression for A and phi in terms of the given quantities, which would be these values and whatever omega is. So in order for me to do this, I actually have to make this kind of messy. I have to expand this thing. I have to expand this term and I have to expand this term. So it's going to be a little bit messy. So I'm going to have to write a little bit smaller. So I got to use the angle addition formula. This one's cosine, cosine, sine, sine. Cosine omega t, cosine phi plus sine omega t, sine of phi. And then this term, I'm trying to scrunch this out so I have more space. And then this one's going to be sine cosine. Okay, so now it looks worse. The next thing I'm going to do is collect all the terms of cosine omega t and all the terms of sine omega t. And I'm going to write the terms here in red. So all the terms of cosine omega t, here's one of them. And let's see, here's another one. And really, here's a third. Then I'm going to collect the terms with sine omega t. And let me use, I'll use blue for that. The terms of sine omega t, this one. And let's see, that one. And this whole thing equals 0. That's 0, okay? So let me double check. I'm worried that I made a math error somewhere because this term is negative and I put a positive there. And I have my notes here that I can double check, so yes, so that's fine. And I forgot one thing. I forgot the L here. Okay. There's a lot of moving parts to this equation, so it's easy to make an algebra error. Okay. So maybe let me draw that. Let me do it in black again. Okay. So this whole expression, no matter what value of t is, this whole expression has to be 0. No matter what value of time is, the whole expression always has to be 0. Remember, I moved this to the other side of the equation. In order for this to be always true, in other words, think of the following. I'll use a different color. Imagine this equation. If this was always true, if this is always equal to 0, independent of time, that would mean B and C have to always be 0. So that means the terms in the brackets have to be 0. I invite you to find an example where that's not true. No matter what value of t is, this thing has to be 0. So that means B and C have to be 0. That means that this term in the brackets has to be 0. So let me go to the other board. I'm going to go to that board. I don't want to come down here. And let's see what we could get out of this. So I'm going to write the term in the brackets. And right away I can cancel out the a's. And I'm going to move this term to the other side of the equation. And I don't want to deal with this minus sign. So I'm going to multiply through by the minus sign. So I get that. So I distribute it through the minus sign. And so what I'm going to do is I'm going to divide both sides by cosine of theta. So sine over cosine is tangent, not theta, but phi. Sine over cosine gives me tangent. And then I'm going to get omega squared minus omega naught squared over r over L. But this L will end up on top. And so I'm going to get omega times L minus omega naught squared times L over R. That's x sub L. This is x sub C. Which is in agreement with the phasor diagrams that we did. Okay, so now we have tangent of phi. I should also say that since I know tangent of phi, and if this represents opposite over adjacent, then cosine of phi is going to be adjacent over hypotenuse. Adjacent over hypotenuse. Or we can write it in these terms. So I can write cosine of phi in the following way. So if I write it in terms of this expression, then cosine of phi is going to be r over the square root of let me double check real quick. Oh, I forgot an omega. Sorry. Okay, I forgot the omega here. And so when I work this through, I get this expression. So this was missing, but this is okay. Oops. That's okay, sorry. Okay, so I made a little error. Sorry about that. So that's cosine of phi, and so sine of phi can be written as like that. Okay, where this is an L. Okay, so I have my expression for tangent of phi, and I think what I'm going to do is I'm going to write it back up here because I'm going to have to go back to that board and work some more. And I'm going to write it in this form. I just wrote it this way so you can see that it's basically the equation we had before. Okay. All right. So let me write tangent of phi up here. Actually, I'll write it down here. So now I want to figure out what this guy is. I want to figure out what A is. So I figured out what phi is in my equation. Now I want to figure out what A is. So I'm going to look at this term in the brackets. And so I'm going to use the red marker. And then I'm going to come over here. And since I'm working on the board, I will tell you here right now that this is going to be a little bit messy. Okay. So I can't really, I'm not going to really show every single step here. I'm going to show you how to get to the actual result, but you should be able to figure that out. Okay, so let me write this term. This thing also has to be 0. So this term has to be 0. And I can solve for A. I know what phi is already. So let me pull out the A from here. And I'm missing an omega. And I'm going to move this to the other side of the equation. So then A is equal to V sub m over L times and again, what I'm going to do here, I'm going to distribute the minus sign through. So I get that. Now, if I put in the expression for sine of phi in there, and I put in the expression for cosine of phi over there, and I distribute the L through. In fact, let me distribute the L through first. Let me distribute the L through. Yeah, let me check my math. Okay. Now, when you substitute these in, you will get the following for A. And I just don't have enough space to write this in. So look, A has this form. Okay? That's A. So that means then that our Q, let me erase this. Our Q looks like this. And I'm going to write it in black so it's easy to see. This is our particular solution. Our Q looks like this. Where phi is given by that expression. And then I, and I'll use a small letter I guess, which is the time derivative of this guy. So this is the amplitude for the current.